All right, so our next video is going to talk about a review of systems of equations and a little bit of modeling. So when we talk about a system of equations, we are talking about how we relate our variables together. So if we have two variables we are solving for, we're going to need two equations. If we have three variables, we're going to need at least three equations. And you can solve a system of equations using elimination, substitution, or graphing. And we'll kind of talk about those methods as we go through and we use a modeling problem to review that concept. So when we talk about modeling, we're not talking about the runway and America's Next Top modeling. We're talking about using math to model something that happens in the real world for us, or sets an example for what we can predict will happen in a real world situation. All right, our real world situation is going to take us in a little bit of a race with a horse. So we have that we can run 0.2 kilometers every minute, and a horse can run 0.5 kilometers every minute, but it takes 6 minutes to saddle the horse before it can start running. So who's ever riding this horse and racing with us, they need to take 6 minutes to get themselves started before they can actually start the running. So the first thing we want to do with a real-world model is we want to define a variable to represent our different values. So here we're talking about a distance that we'll run, and we have that compared to a time for which we are running. So you can pick whatever variables you want. Usually we go with the first letter of the word for what we're talking about, but you also can just use X and Y. In this case, our time would be X and our distance would be Y, because time is happening independently. Our distance that we run depends on how long we've been running, so our distance becomes our dependent variable. I'm going to choose to use D for distance, and I'm going to use T for time. Whoa. So time, distance. But again, if you like to work in the world of X and Y, totally cool. Our distance is dependent, and our time is independent. So it's up to you. When we think about a coordinate pair, then we're talking about time, comma, distance, or X, comma, Y. You can pick which pair you want. I'm going to go with T and D, time and distance. So if you want to stick with me, I would suggest writing down those variables. All right, so it says create an equation to represent the distance you have traveled with respect to time. So I want you to pause your video and see if you can come up with an equation that represents the distance as it relates to the time that we've been running. Pause your video and write that equation now. So you might recall from some previous classes, or maybe in science class, that we know that the relationship distance equals rate times time exists for us, right? So our distance is how far we've traveled, the rate is the rate at which we're traveling, times how long we've been traveling. So if we think about that with our variables, distance was D, our rate at which we were running was 0.2 kilometers per minute, and our T represents our time. So the next thing says create an equation to represent the distance the horse has traveled. So distance the horse has traveled with respect to time. Keep in mind that our horse didn't start running until 6 minutes after you did. So again, go ahead and pause your video, see if you can reason through that and come up with an equation to represent the distance the horse has traveled with respect to time. Pause your video now. All right, so I would say there's two different ways you can think about setting up this equation. The first way is getting this distance equals 1/2 t minus 3. And that comes from thinking about writing our equation in the form y equals mx plus b. So we know our y value is representing the distance. We know our rate, or our slope, rate of change in slope, is 0.5. And we know time, and what we would still need to find then is our y-intercept. What is this b value? Well, we know that the horse takes 6 minutes before it starts, so it goes through the 0.60. Well, if I apply that 0.60 to help me figure out my b value, I end up with 0 equals, sorry, that should be a 3, plus b, which means that b is equal to -3. I go back to this structure, and I can plug in my distance, my rate of change, time, and my y-intercept. The other way to think about it is looking at your distance is equal to your rate times your time minus 6 minutes. Because whatever time we start with, we have to subtract 6 minutes from it because it takes us 6 minutes to saddle the horse to get going. Okay, so you can think about this as you're reducing your time by 6 minutes when you start. And if you notice, when you clean up this equation, you get the distance equals 0.5t minus 3, which is this same equation right here. Okay, so either way you want to think about the setup, your time reduced by 6 minutes, or working with the y-intercept to find the y-intercept using the x-intercept of 6, 0, that's totally fine. But no matter what, we should get to this equation of 0.5t minus 3. All right, assuming you and the horse are running along the same path, does the horse ever catch you? If so, when? If not, why not? So we had two equations. We had our distance equals 0.2 times our time, and we had the distance of the horse equaled 0.5 times our time, lowered by 3, right, for our y-intercept. Well, if I look at this, I have two variables that I would like to solve for, distance and time, and I have two equations that relate them, so I can use a system here to solve. So the first method is talking about elimination. If I were to take this equation and I were to eliminate the variable d, I could subtract one equation from the other. So distance minus distance, that's going to result in a 0. 0.2 minus 0.5 is negative 0.3t. This is technically a 0, so 0 minus negative 3 makes a plus 3. Well, now I've eliminated the distance variable. I'm just looking to solve for t, so I can add this to the other side. Solve for t by dividing by 0.3, and I find out that t is equal to 10, which we were measuring in minutes. Then using the fact that t was 10 minutes, I can go back to my equation, either one. I'm going to use the first one just because it's a little bit easier. I just found that t was 10 minutes, which means that my distance, I should keep that in red, my distance is going to be equal to 2 kilometers. Okay, so that's using the elimination model. I've taken my two equations, I have eliminated a variable so that I can solve for the other. Then what I've done is gone back and applied that variable into either one of the equations. If you plugged it into this one, you would also get a value of 2 for your distance to get my other variable. So the other method is if I start with that d equals 0.2t and d equals 0.5t minus 3. Another way to talk about this is using substitution. Well, substitution is when you isolate one variable. So here I have d isolated, and that variable is equal to 0.2t, which means in this equation where I see d for distance, I can replace it with 0.2t. I am substituting in one variable for how it relates with time. From here then, I can solve this. If I subtract this 0.5t to the other side, I get negative 0.3t equals negative 3. Solve for t, I still get 10 minutes, right? If you divide by the negative 0.3, 10 minutes, I can plug it back into either one of these equations, and I still get my distance of 2. Okay, so we had elimination, where you eliminate a variable. We had substitution, where you isolate a variable, which in this case it already was for us, which was kind of nice, and then substitute that into your second equation, so everything is in terms of one variable. Work to solve for that variable, then plug in that value to one of the original equations to find the other. Our last method then that we talked about for solving a system of equations is using graphing. So here it says to graph your two equations on the same coordinate plane. So I want you to graph your running value, your running model, and I also want you to graph the horse's running model, and then we will compare our answers. So go ahead and take a second and graph those two lines that we found. The first one is your running model, the second one is the horse's running model. All right, so let's see how we did. I have your running model and the horse's running model graphed here. So your running model went through 0, 0, had a slope of up 2 over 10, right? That 0.2, or you could view it as up 1 over 5. The horse had a y-intercept of -3, so if you follow this line back, you'll intersect with -3. You can also think about that moving over 6, right? 6, 0 is where we started the horse running, because the horse didn't start running until the 6th minute, and then it had a slope of 0.5, so up 1 over 2, up 1 over 2. So, thinking to yourself, why are we only looking at the graphs in quadrant 1? Go ahead and think about that for just a second. Hopefully you came up with the fact that time is positive and the distance that we're running is positive, in which case we only need the first quadrant to be looking at our real-world model. The next thing says, what does the point on the graph where the two equations intersect represent in the context of the problem? Well, here's our intersection point. That's the point 10, 2. If you think about 10 was measured in time, right? 2 was measured in distance. So this was minutes. This was kilometers. Why were 10 and 2 important for us on the previous slide? Well, Ms. Schwartz, of course. When you look here, at 10 minutes, we had run a distance of 2 kilometers. Do you agree that your line, your running, after 10 minutes, you had run a distance of 2 kilometers? So the point on the graph, the intersection, represents the point at which our two equations were equal. Right? We came up with an answer of 10 minutes, 2 kilometers. All right, so how far did you travel before the horse caught you? And how long did it take the horse to reach you? So if we think about how far you traveled before the horse caught you, we knew we had this point, this important point on our graph of 10, 2. So your distance that you ran was 2 kilometers, right? You were at the 2 kilometer mark when the horse caught you. But I want you to pause and think and look back at your graph and see if you can figure out how long the horse was running before it caught you. So go back to your graph if you need to, and think for a second about how long was that horse running. Go ahead and pause your video and think about it. Okay, so hopefully you look at your graph and you say, well, the horse started here. The horse had to run this far to get to our 2 kilometer mark. Well, how long then? What time did it go? How long did it take, or what time did it take to get from 6 minutes to 10 minutes? The horse only ran for 4 minutes. You ran for 10 to get to the 2 kilometers. The horse, though, it only took 4 minutes for him to catch up. All right, so again, system of equations. We go way back. Elimination, where you eliminate a variable. Substitution, where you isolate and then substitute in. Graphing, you're looking for a point of intersection, x, y, that will make your solution true. That's it. I hope you had fun with modeling. There will be more coming up, don't you worry.